So that brings us to the first speaker of today's session, who is going to be Priyesh, who's going to be giving us an update on his talk about skew spectra. Take it away.
Hello everyone, can you hear me? Fine.
Yep.
Right. Hello everyone. Thank you for watching my video. My name is Priyesh, and I presented on the CMB cross LSS skew spectrum. So basically, what they were was it's a cross correlation statistic between a quadratic field that you can see over here, D, that's computed by convolving two density modes in a harmonic space with some convolution kernels and cross-correlating it with a single density mode. And these kernels you can see on the right, they're determined by these Legendre polynomial shapes that come from the gravitational bispectrum and angular space. And the important takeaway message is that using these skew spectra for Desi cross Planck at least, we were able to constrain cosmological parameters, which are non-amplitude parameters, to up to 17% less accuracy than the bispectrum. And these are some example skew spectra on the right for some L60 specifications. The other major thing that I would like you to remember is, oh, sorry, is there a question already? Is there a question from Robert?
So your 1 minute is up. So we start the discussion session now. And then do you want to finish with the final sentence?
So, yeah, sure. Sorry, I thought there was a question, so I stopped midway. But right, so the next main thing that we did was write down an algorithm to compute these skew spectra from the data, which takes n log n steps, and we tested this on a sample simulation suite, the massive new simulations, and we constrained the linear and quadratic biases along with a short parameter. You can see our constraints on the right. Right. Anybody has questions?
Okay, so if you have questions, then feel free to raise a hand. First one up is Robert.
Yes, thanks, Presh, for the talk. I was wondering if you can give any kind of physical interpretation, any intuition for why, for example, these specific definition of spectra, the skew spectra, capture quite a bit of the information in the bispectrum, especially in the sense of, is there some intuition that could be used to even improve on that? Maybe there are even better, similarly efficiently computable quantities that you can use to gain even more out of this. So if there's some kind of guide that one could use to improve on that, even maybe.
Sure, thank you for the question. Maybe I can illustrate what's kind of what we think is happening by just going over what the skew spectra actually are optimal for. So the skew spectra are designed to be optimal for amplitude parameters. So it's derived using the standard FNL estimator that you can see over here. So that's when the convolution kernel is, when you pick it to be the full theoretical bispectrum, then the skew spectra will be optimal for the overall amplitude of the bispectrum. Now, what we're doing is something a little bit different. We're writing down the angular bispectrum in terms of these Legendre polynomial shapes, where it's not quite the Legendre polynomials themselves appearing in there, but a line of sight projection of them because we're in harmonic space. But at least in redshift space, if you were to use the Legendre polynomials themselves, then what you can show mathematically is that each of these skew spectra, like the tilde CL for each of these Legendre polynomial shapes, are sensitive to just the prefactor, the combination of biases appearing as a prefactor in the full expression for the bispectrum. That's not exactly true in harmonic space, but this is kind of the intuition that the physical intuition for what approximately is happening for each of these skew spectra. Does that help answer your
It
question?
helps. Yeah, it helps definitely. But I mean, if you wanted, basically, you would have to, if you have a specific other type of parameters in mind, you could follow a similar procedure to optimize for that.
So I'm not sure how this would work for non-amplitude parameters. But if you have, so the strategy I can imagine would be, if you have a specific amplitude parameter you want to constrain, then you want to isolate some sort of the shape for which it appears as a prefactor, and check whether that shape is orthogonal to the other shapes that are entering the bispectrum. If that makes any sense.
It makes a lot of sense. Thanks.
Thank you.
Okay, next we have Hector.
Hello there. Can you remind us how do you estimate the covariance for the skew bispectrum? It's an analytical covariance.
For Fisher focus for this, you mean for this plot? No, sorry.
Yeah, I mean for the Fisher focus, you need to assume a covariance, right?
Yeah, we used an analytical covariance.
But how do you account for the off-diagonal terms?
So the theoretical the theoretical covariance, which you can see over here, which is it's an expression that tells us the off-diagonal terms as well. So I'm not sure.
Yeah. So this, sorry, I'm not very familiar with this notation. So I wasn't sure whether this was including the LSS Q bispectra or what is just for the power for the 2-point part.
So each block in this plot represents the covariance between the skew spectrum with the zero Legendre polynomial kernel and the zero Legendre polynomial kernel. So this is that one. So for between the covariance between the 1 and the 0 shape is this one, and the 1 and the 1 shape is this one, and each of these squares are populated by L's on each axis. So this line over here is the diagonal for the covariance between the 0 and the 0 shape. This line is the diagonal between for the covariance between the 1 and the 0 shape. Does that make sense?
I mean, yes, I guess so. I mean, as I said, so I'm not very familiar with this notation, but I guess it does. So, however, it's a bit difficult to check whether this is diagonal or not, because you are actually plotting the actual covariance and not the how do you call the terms, like the diagonal, the non-diagonal element divided by their diagonal corresponding in such a way that what is lies along the diagonal is by definition 1, and what it's outside the diagonal, it's a number between -1 and +1. There you can check how non-diagonal is the covariance, and from this picture, I really cannot tell anything, because they are like very there are numbers that they vary a lot in a very large range, and which I don't understand. But okay, I guess I mean, if you have that plot, that's fine.
You should, I guess, to check whether I mean, it depends on how well you want to see the off-diagonal terms, but what you can see is, what you should compare is this line in each box with the points to the left and right of this line, and each of these, and you should do that for each of these boxes. So you can, for example, for the H2 covariance, you can tell, okay, the diagonal clearly dominates over the off-diagonal pieces, but the same is not true for the 8080, for example. What we found in our focus was, when we don't include the off-diagonal pieces, then the forecast is really too optimistic. So we really found that we had to include these off-diagonal pieces as well in order to get realistic errors.
Okay, thanks.
Thank you.
Okay, we don't have any more questions for Prish. So I think with that, we'll thank Prish. Everyone use your little emotive happy clappy hands. Excellent. And we will now move on to our second talk, which was Alex.
Okay. Okay, great. Hi, everyone. I'm Alex Kralewski, and my work was on cross-correlating Planck CMB lensing with unwise galaxies selected from the unwise infrared catalog. And so I just pulled out this slide for my talk, which summarizes the cosmological constraints that we get. So we have 3 samples of unwise galaxies, blue, green, and red in order of ascending redshift 0.5 to about 1.5. And you can see here the constraints on omega matter and sigma 8 and S8. And you can see that the samples overlap each other well, which is great. And they're a little bit lower S8 than Planck. So yeah, I think we can start the discussion.
Fantastic. Thanks very much, Alex. So if you have questions for Alex, please raise your hand. I might kick off, take the chair's prerogative. I noticed in your slides 9 through 11, where you were showing the ineffective maps of your sample, there's still apparently a bit of systematic variation in number density as you approach the galactic plane. And considering that you said you have a GG component that you include in order to combat bias calculations, I was wondering if that's an issue.
Yeah, that's right. So in addition to this analysis, I also took my galaxy maps and regressed them against a bunch of imaging templates, including stars and as well as WISE depth maps. I mean, I guess this galactic trend is probably more related to stars. Even when I applied those weights, we had very similar power spectra. I think, this probably would change the GG power spectra, but we're cutting it to use only L greater than 100. And so sort of at those scales, this trend doesn't have much impact.
Okay, cool. There's a follow-up question from Yun Ting.
Hello.
Hi.
Hi. Yeah, so my follow-up question is, so it's on WISE catalog, have a very uniform depths in all their colors, or otherwise you might have maybe different selection bias on different part of sky. And like when you cross-correlate with the tomographer, I remember it mostly covered only the northern hemisphere, but not the south.
Yes, sorry. At the beginning, did you say that, were you asking if unwise is uniform, or were you saying that it is or isn't?
Yes, I'm asking if it is uniform, so you can make sure you, when you cross-correlate with the tomographer, and that only cover part of the sky, and you can generalize your estimate to all your samples.
Right. Okay. Yeah. So it's not uniform. So WISE has a scan strategy where they cover the ecliptic poles more than the ecliptic plane. So there is a fairly large change in galactic latitude. Ecliptic latitude because of this, and ecliptic depth. Now we restrict our sample to the completeness limit at the lowest coverage at in the ecliptic plane. So, that sample should be complete everywhere. We don't see much of a trend with ecliptic latitude. Like I said, when I applied these weights, I also didn't see much trend in the power spectra. But yeah, we are, it is concerning that, yeah, the spectroscopic samples are biased on the sky. So I also tried, as a test, restricting the cross correlation to the region where we have the spectroscopic samples, and that gets consistent results. It's not the most discerning test because you're throwing away 60% of your data, so the error bars are rather large, but at least suggests, I don't think we have any evidence to think that there's a big change between the spectroscopically calibrated region and the full sky.
Okay, got it. Yeah, thanks. Yeah, it's great you have done those kind of tests. Thanks.
I have a follow-up question on the clustering redshift distributions that you generate. One of the main issues that we worry about in clustering Z's for cosmic shear studies, for example, is negative amplitudes and how you reliably treat or robustly treat negative amplitudes. I noticed in the generation of the N of Z that you have, the model that you've used essentially just truncates the N of Z to be positive. Have you explored what effect that has by treating differently the negative amplitudes to the positive amplitudes, because you end up with fluctuations around zero that are artificial?
Yes, we did. So first of all, we studied this in a mock DNDZ where we generated the DNDZ, we put in some noise, and then we did this truncation at zero. So you are, expecting only to have noise fluctuations going up and not going negative. And then we looked at how that affected your theory predictions for the CLs, given that your redshift distribution is now a little bit biased. And so actually in our theory prediction, we subtract off this bias, which turns out to be very, very small. The other thing that we did is we wound up truncating the N of Z's at relatively high redshift because there we were seeing some noise fluctuations in the clustering redshifts, but we were seeing when we cross-matched our WISE galaxies to deep photometric redshifts from Cosmos, we found no matches at those redshifts. So we removed those fluctuations from the N of Z. We set it equal to 0.
Okay, Prish.
Hi, thanks for your talk. I was curious about this, the choice of not varying the higher order bias parameters. But I guess I'm curious what you selected as your B2 in BG2 for your analyses, and how sensitive your results were to your choice.
Yeah, so we set B2 using coevolution relations that were taken from a separate universe simulation study of higher order bias terms. Yeah, and so how sensitive are our results? So if we free up B2, if we allow it to be entirely free about this relation, and basically give it a linear offset in redshift so that it's, at any point it could be lower or higher by a certain amount. We found that change in B2 is a bit degenerate with S8. So it is something that we're sensitive to, yes.
But is there a choice that makes you consistent with that?
Yes, if we have a relatively extreme value of B2, so if it's delta B2 is -2. So like it's 2, B2 of Z is less than the fixed coevolution relation by 2, then that is close to being consistent with Planck.
Thank you.
Okay, thanks very much, Alex. That's all the time we've got for you. So everyone, hands together. And up next, we have Louis. Louis, if you want to prepare your slide.
Okay, so wait a second. Not this one. Yes. Okay, so hi everyone. So my talk was about iterative methods to reconstruct the CMB lensing power spectrum. So in the future CMB surveys, we will reach very low noise and polarization. So optimal methods like this iterative reconstruction will be better than the quadratic estimator. And in this talk, I showed how we developed a simple and robust end-to-end pipeline to get optimal estimation of the lensing spectrum. So basically, we estimated this N0 and N1 bias terms. So these are terms that bias the lensing power spectrum that you reconstruct from a quadratic estimator, but also from our map, so maximum a posteriori reconstruction. And I showed that we get a factor 2 lower N0 bias and a factor 4 lower N1 bias. And I also showed that we use like a very standard likelihood, like the same in the Planck paper, but for our map reconstruction, and we get unbiased estimates of cosmological parameters. So here it's a marginalized constraint on the neutrino mass for fiducial cosmology and for a biased cosmology, and in both cases we reconstruct it. We can estimate the mass in an unbiased way. Yeah, so that's my summary.
Super. Thanks very much, Louis. Excellent timing. If people have questions for Louis, raise your hands. And I might kick off with as a complete outsider to this field and knowing very little about it. I was wondering, in your end-to-end pipeline, do you have to consider, for example, marginalizing over observational systematics in your data vector? Is that something that you include in the end-to-end pipeline?
So no, we don't marginalize over observational systematics. So what we use is to get robust towards this observational systematic is what is called RDN0. So I have a slide for this RDN0 here. So this RDN0 is a combination. Let's say here. So it's a combination of simulations and data CMB maps, and you reconstruct for the quadratic estimator. You reconstruct the CMB lensing potential by combining two CMB fields. And for RDN0, instead of combining two data fields, you combine either a data field and a simulation field, or two simulations. So these are DI or IJ here. And you can show that in this way, you can cancel the assumptions that you made in your reconstruction towards, for instance, the noise level of your experiment or the fiducial cosmology of your CMB. And here it shows that if you debias with N0, so this N0 is an analytical calculation of the 4-point function of the CMB that enters into the lensing power spectrum, you get biased results. So these are the triangles here. So in green is for a very large atmospheric noise. In red is when you assume that you have a lower lensing amplitude than the real one. And in brown is when you assume strange wiggles in the lensing power spectrum. And if you debias with N0, you're totally biased. And if you debias with this combination of data and simulations, yes, RDN0, you get much closer to the truth. And this blue line here is a cosmic variance of for CMB stage 4. And so this exists, this is a standard approach for the quadratic estimator, and we have the same for the map. So this plot here is for the map. And we also combine on one leg data and on one leg simulations, and we show that it works the same as for the quadratic estimator. Yeah, there's a lot of technical terms, so I'm sorry for that.
No, that was very well explained. Thank you very much. So again, if anyone has any questions, feel free to raise a hand. Well, then I'm going to go again. I have a question. Oh, no, Robert, you beat me to it. Go ahead.
Yeah, thanks. Thanks, Louis, for a talk. I have a question regarding just the method of the iterative approach. So I'm not sure if I completely got this. I have a question might be naive, but as far as I understood, so each iteration you use the QE as like a non-optimal estimator, and then while iterating you improve upon that to actually approach the true maximum. So is this guaranteed in principle to converge to the true maximum a posteriori, or is there something that depends on the choice of your intermediate estimator, like the QE in this case?
So there is no total guarantee that we get to the maximum of the likelihood, because we can get stuck like in a minimum likelihood, like a local maximum, and but we did some tests, and for instance try to get a bit different starting points, and it converges to the same point. So we think that we can reach the global maximum. And I don't know exactly if it can depend on the intermediate steps. So the way we do is you write the likelihood of your lensing potential given what you observe, and you try to maximize this, right? And to maximize it, you compute the gradient of the likelihood. And in fact, if you develop the gradient of the likelihood, you can show that it's equal to having a quadratic estimator with some modified weights inside. So this quadratic estimator with modified weights is actually the gradient of the likelihood between at each step.
I see.
So
okay,
the
so
weights are, yeah.
So it's not a free choice,
really.
It's something that drops out of your method, and then just that happens to be this one. Okay, I see, that makes a lot of sense. Thanks.
Exactly. Yeah.
So again, feel free to raise a hand if you have any questions. So I'm curious about your forecast for the CMB stage 4. These look very good. I'm wondering if any of that forecast is particularly optimistic, or do you think that's particularly pessimistic?
I think they're quite they're very standard in the community, because they correspond to the forecasts that were published in the 2016 paper of the CMB stage 4 science paper. And maybe they're a bit optimistic in the sense that it assumes that there's a DAISY BAO likelihood that is joint here, that is used to combine the joint analysis. Might be a bit optimistic, because I don't know much about the particular systematics in the DAISY survey, and this comes from a forecast paper also. So I think they might have been optimistic in this sense, but I don't know. And then for CMB stage 4, I think it's these are the noise levels that are expected to be reached by CMB stage 4. Probably we get more realistic when we get closer to the survey, but I think they're quite realistic for now.
Thanks very much. We've got time for another question if anyone wants to put up a hand. In that case, we'll thank Louis. We'll put together your little clappy hands.
Thank you.
And up next, we have Pablo.
Hello. Hi. Sorry, my computer just, of course, had to freeze at the moment that. Let's see. Sorry, technical problems.
If you prefer, we can go to Tillman and come back to you, Pablo.
I think I got it. I think I got it now.
Okay.
Let's see. Yeah, there we go. Yeah, so that was my summary slide. Yeah, so I'm Pablo. I'm talking about simulation-based inference, which is slightly different from other people's talks. The idea is that in simulation-based inference, instead of using a likelihood, we use simulations to do inference. And we're talking here about how when we use spatial neural networks, generalizing over neural parameters, you get more robust results in the case of limited simulations and imperfect simulations that don't perfectly match the data as you expect for realistic applications. So we tested on the case of the CMB power spectra, where we have theory and we can generate simulations with the idea of understanding how it works for when we go to cases where we don't have theory, such as high order summary statistics from galaxy surveys and so on. Yeah, that's about it. Paper will be on our archive on Thursday if people want to follow up, and of course my talk is in the video as well. I think that's about a minute.
Great, you've nailed it, a minute exactly. If anyone has any questions, please raise your hands. I might kick us off with a question that I had after watching your talk and also heard from on Slack from Min Feng Hu, who asked, how many sims do you think are needed in order to reach the same performance as the likelihoods? You demonstrated.
Yeah, that's a good question. So yeah, I guess that's following. So like this kind of plot, you have the likelihood base. So when we have access to CAM and we can run it as many times as we want. And the yellow and red are using 10,000 simulations. So we run CAM 10,000 times at random cosmologies. And we use those to do inference. And yeah, we didn't actually keep increasing that number until the ellipses match size. We obviously know that the less simulations you have, the bigger your error, because you add like an extra source of error from the fact that you're doing inference from a limited number. It's an interesting test that we could try to do actually, maybe for the next version. I actually don't, I mean, Jesus, whose hand is up, will know better. I think for when you do an MCMC, you do end up doing order like 50,000 likelihood calls, but that's also kind of smartly chosen, whereas these were randomly sampled for the prior. So I imagine you will need, my guess would be maybe like 100,000 to get the same size. But yeah, I don't fully know.
I think that's a really interesting question. And I think also it's interesting in the context of the bias that you find using the SWA and not.
Yeah.
It might be interesting to see if you can ratchet up the number of simulations whereby the systematic bias between choosing to use the SWA or not is catastrophic, right? Could be really negative.
Yeah, the reason we picked 10,000 is because obviously this is the thing in mind here was to try to do inference using the Quixote set of simulations, which for whoever might not be familiar, they're simulations of galaxy of dark matter on 10,000 different cosmologies. So you, sorry, I think it's 2,000 cosmologies, but 5 simulations per cosmology. I don't actually know off the top of my head. It's 10,000 simulations. So the idea was to have that number of simulations, which is the ones we have if we try to do simulation-based inference there. And we get that, yeah, it's not quite enough that to get optimal contours, but you can still get contours with simulation-based inference that could be interesting, because obviously the point of simulation-based inference is that you can use summary statistics where you don't have access to a theory prediction, and then you can try to break degeneracies by doing that.
Great. Jesus.
Hi. Hi, Pablo. First of all, I think that the fact that you have a limited amount of simulations, you really can account for them by making the contours bigger. It's super cool that this can be accounted for, and it shows us actually, and it's actually computed correctly as a source of error. I think this is really great. And I have a general question in this kind of methods. So you have shown that this would be robust against an unexpected effect on the data. And how is that related? How do you see that related with this unexpected effect on the data being actually a physical effect?
It's a very good question. I mean, yeah, the idea of testing that came from, yeah, like if we try to do again, if you try to do Quixote simulations, you do some kind of forward model to predict, imagine the, I don't know, the boss galaxy distribution. We know that our forward model and our simulation are not perfect. They will not be exactly like the data. So when we put the data to this pipeline, there will be differences. So yeah, we try to put it as in like a bit of extra noise in a certain multiple range. I mean, obviously this is a very simple data set compared to an image, but it's something that we probably want to test more before trying to actually do inference on things where we don't have on more complex data. Because yeah, whether it comes from a physical thing, I mean, obviously there's a limiting case where you, if there is some kind of effect in the data that's not in the simulations that looks like changing a parameter, then obviously there's nothing you can do because then, so imagine that there's, I don't know, like a dark matter species that what it does, it looks exactly the same as changing, I don't know, the neutrino mass. If I then try to inference the neutrino mass, then
it shows us up a bias, basically, right?
Exactly, it will just give me a bias. So what we try to do is the thing that we probably can account for, which is like, oh, maybe there's an extra systematic, or there's an extra source of noise, or there's something like that. But yes, I think the main challenge of this kind of thing on more complex data sets is to get simulations that look as close as possible to the data. Okay. But it's nice to try to be more robust to the fact that is never going to be exactly the same.
But then there will be a follow-up question. In the case in which the effect is degenerate with some of the parameters that enter the set of simulations that you have produced, a metric on whether this is actually a bias of the method would be kind of to be able to estimate the difference in size between your contours that take into account the size of the simulations and the expected size of the contours, even if you don't know where they are, if you had done likelihood-based inference. Is there any way that you can compute this, at least have an order of magnitude sense of this shrinkage?
Well, that you can do that here because you have the likelihood base, right? But I guess the point is to take it to cases where we don't have the likelihood base.
Yeah, but you know the tendency, right? It seems to me intuitively that there could be a way at least to get an order of magnitude estimate.
Yeah, we could talk about that more, actually. That could be a good idea. We hadn't thought, because you could use some kind of KL divergence to measure the size of the ellipses. Yeah, that could be an interesting idea. We'll talk about that.
Okay. More. Thank you. I may have another question.
Yeah, send me
there is time and no one has
message. Yeah.
Okay, sure.
Robert has his hand up, so if his question is quick, or Robert, go ahead. Take as long as you need.
Sure. Yeah, I was also wondering about the. I was wondering if there's any crosstalk between the compression and the normalizing flow in this case, or if you have like. It sounded to me like the compression is a complete separate step, and then you deform this with normalizing flow. But I'm wondering if there could be crosstalk and if that could somehow help to find a more optimal compression.
Yeah, that's a fantastic question. So that's referring to, for whoever didn't see the talk, the idea here is that we do first a data compression step, then a normalizing flow. And yeah, we've talked about how when you marginalize, ideally you would want to do all of this in one go so that you can then marginalize, because there will be cross correlation between these two. Yeah. So we know that this is in that sense imperfect. We would want to ideally do both. We haven't yet managed to implement the marginalization normalizing flows just because they're slightly more complex. But once we've got that going, we will try to do this in one step so that you can account for cross correlations, which will definitely be there. So that will affect things a little bit. I don't think it will be a huge effect, but it's definitely something that we should do. It's a very good question.
Okay, cool. Looking forward to that.
Okay. Jesus, is the question quick?
Yes, I think so. Well, the question is quick. I wonder whether the answer is quick. So there are three main costs when you try to do likelihood inference, or three main problems when you try to do likelihood-based inference. One is the cost of the computation of the observable that you want to compute, which is cost, is time. The other one is the time that it takes to compare this to the data vector. That can be big if the data vector is huge, like the bispectrum, for example. And then there is one which is not necessarily in terms of cost, but of difficulty, which is to have the correct statistical modeling of the noise. And you sort of mentioned this third one when you say that you can not do, for example, do moped because you don't have the noise covariance, but you do need to have the noise covariance if you're doing simulations, right? If you want to simulate also that you go through the pipeline of the experiment, you do have to already have this statistical model,
Yes. No.
right? So
What I meant.
you can
Oh,
somehow
go ahead.
have it?
No, I mean, what I meant was, I mean, it's a few things. First of all, well, I think what I meant was more that, yes, you will have some kind of, again, imagining, in this case, we have the noise covariance, obviously. Again, what we're trying is to imagine putting ourselves in, if imagine my input data was, like a Boss galaxy map or something. Obviously, I'll have things like shot noise and stuff. The problem is that to get covariances, I will need so many simulations that it's just unfeasible. Like a simulation is really expensive. So I can add noise to an individual simulation, but it's really hard to get enough, to run enough simulations to get a covariance matrix. Not hard, it's just impossible. As in we don't have the resources. So the idea is that, was that, sorry?
Sorry, Pablo, I was just going to say, I think that with that depressing endpoint, we might prolong the remainder of this discussion to the.
Yeah, happy to keep on discussing offline.
Fantastic. So everybody put your hands together for Pablo. Thank you very much. Sorry for having to cut you short. And our last speaker of the session, everyone little clappy hands, good. Last speaker of the session is going to be Tillman. Pablo, you might need to stop sharing first, I think. Oh no, yeah, great, there it is. Excellent. Off you go, Tillman.
Great. Right. So what we did in this little talk was do a joint analysis between Kitz 1000 and cosmic shear and the cross correlation between Kitz 1000 and the TSZ effect. The idea was originally to constrain baryonic feedback, but that evolved with time to this joint analysis. And as I'm showing here, we actually got interesting, at least, cosmological constraints that shows that in future data like grouping and Sun observer, we could get really interesting constraints from probes beyond just the standard 3x2 point, and as a byproduct, also get a better handle on baryonic physics. But I mentioned some of the caveats in my talk, and that's it.
Excellent. So if people have questions for Tillman, then please start raising your hands. I thought I might start us off with a very quick clarification question, Tillman, of what is PPD and TPD for those who don't know.
So PPDs are posterior predictive distribution, so that indicates on if you were to redo the measurement, then you would expect your measurement to lie in that gray band. So if your actual data measurements lie outside of that, it indicates that there might be an issue with internal consistency. And TPD is, I think, translated posterior distributions, and that is basically taking samples from the posterior and plotting the corresponding model prediction. The difference between the PPD and TPD is that the gray band, you add in the additional noise from the data vector, and the curved line here are just the model predictions.
Excellent. Robert.
Yes, thanks, Tillman. I have a question that harks a bit back to the baryonification discussion yesterday. So if I got it right, that the cosmic shear constraints on their own here, they just exclude those data where baryon, where just too much uncertainty due to baryonic feedback. So do I already have some idea on how much, if you use something like Giovanni's Bacco, that helps you to model these scales and then marginalize over the current uncertainties we still have, how much improvement could be gained on cosmic shear alone, or is it currently still too unconstrained if you marginalize over it? Any idea? I'm not sure if you looked into this already. But...
No, so we didn't. So we tried in the course of this paper, we actually tried what happens if you push to smaller scales, because I said we wanted to constrain baryonic feedback, and that actually didn't, because we stuck to the relative conservative scale cuts we had for Kitz 1000. So conservative meaning up to L of 1500. So not conservative by other standards, but for cosmic shear. And I mean, you gain a bit, if I remember correctly, but even then we didn't push too far, like then to L of 3000 or so, and mostly looking at the cross correlation. But I mean, yes, you could do that. I have reservations if you want to do that with the current modeling setups we have, because I think there's a lot of intrinsic uncertainty on how much we understand these effects on these very small scales.
Right. I might have a quick follow-up then. If you have these concerns right now, what do you think would be needed to, well, get rid of those concerns? What is missing?
I think we need probably a more hydrodynamic simulations that are catered to what we need as cosmologists. So like big boxes that we have representative big halos, that we can measure the power spectrum even out to larger scales to see that it converges and so on. Right now, many of the simulations are by and for galaxy evolutionists, I guess. And they have slightly different interests on what science they want to look at and what the simulations cater for. So we need more bigger simulations that cover maybe a wider range of feedback models and subgrid models to make sure or make us more certain that we don't miss something in these models.
Okay, got it.
Giovanni has a follow-up.
Yes, I was wondering if these concerns are more in the shear part or in the Sunyaev-Deutsch part, or in both equivalently, or like which one you see is like the most complex to capture for the current modeling?
I think the shear part is comparatively easy. So I think Marcel van Dalen made a very simple toy model where he just moves particles out of halos below a certain mesh threshold, and that is surprisingly good at reproducing like this power spectrum suppression. And in the baryonification model, where you just push out your particles from some central halo with a very simple prescription, works extremely well, right? But for the baryonic probes, especially TSZ, where you're sensitive to the gas temperature, that's a lot harder, and especially harder also to measure in simulations. So for this work, especially the autocorrelation of the SZ effect, the Bahamas simulation, which are quite big with 400 megaparsec boxes, are basically already too small to really resolve these big halos often enough to have a statistically representative sample.
So I have a somewhat related question. Those two questions were both focused more on the modeling side, the simulation side. I'm wondering, in your opinion, what surveys, observational surveys, would be required for us to be able to put a very good, accurate estimate on baryon feedback using something like cosmic shear and TSC? Do you think stage 4 will get us there?
So I have high hopes for not TSZ, but for the kinetics Sunyaev-Selvovich effect, because there you don't have the temperature, you measure the gas density directly. And from what I've heard and the forward I've seen for something like DESI and some observability or even CMB stage 4, you can basically measure all gas profiles for any halos you want to precision. That's very well good enough for what we would need for cosmic shear. So I've hoped that can be solved. There's obviously problems with selection. In fact, if you measure the same halos and so on, and also because everything is full sky, we have overlapping surveys, so you can't just independently measure baryons and then apply it for cosmic shear and do a big joint analysis, or at least account for the covariance of these different measurements. But I think, yeah, kinetic Sunyaev-Selvovich effect is very promising, and you don't need to deal with some of the nasties that you have in X-ray measurements of gas fraction and so on.
Okay, are there any other final questions for Tilman? Then in that case, everyone put your hands together for Tilman. Thank you very much. Thank you very much to all of the speakers from this session.